I'm also gonna, I tested it, yeah. Yeah. I'm also gonna start streaming now. If someone wants to, they can confirm that the stream is live.
That is working. Okay.
All right, everybody. Okay, I'm not sure who feels like watching, but I'm gonna give my talk. It's actually gonna be kind of a long one. I'm gonna hope to try to run through things, and because I'm gonna be moving quickly, I want to get people's feedback, just raise questions, and tell me if you're confused or want clarification or just have a question in general. I can grab it, it's fine. You guys gonna make me stare at you guys through the wall? Except for you, 𝗣𝗿𝗀𝗀𝗃, thank you, front and center. Oh yeah, but then you have to be back here. That's fine, I'll stand here. Plus I like to see my slides. Well, I guess my slides are everywhere. All right, well, this is a intro to System D. I actually ended up writing a decent amount about how System D worked under the hood, but really the goal with this is that you can walk away knowing how to administer it and use it on your system, and that when something goes haywire, you just don't throw your hands up. You kind of have some tools. So, with no further ado, source code, all examples shown in this, all on the GitLab server. I also dropped it on the coordination. I did not proofread these slides. I finished these like an hour before I showed up, so forgive some typos or other mistakes. I already talked about goals, but here's a list again. I think we'll hit all of these. Yeah. The first one is, I spent way too long on this, so I'm going to run through it, is the Linux boot process. We're going to scream through that. Hopefully people are already familiar with it. Okay, so Linux boot process. Only reason I want to talk about this is I kind of want you to know how we got to System D instead of just here we are. So, as a quick summary, most systems will have, well, they definitely will have some sort of boot ROM or flash. You get there, first thing, the CPU hits a reset signal and pulls something out of the boot ROM, starts these two bootloaders, kernel and init. We'll go into those more detail except for the boot ROM. No one cares about that. So first stage bootloader is usually very highly system dependent, but probably everyone here has a IMB PC compatible x86 64 computer. So you're probably using, all right, William doesn't. I knew one person had a RISC-V laptop, so they don't. Or Mac OS is ARM. Anything ARM that's going to probably use ARM trusted firmware and its own boot process.
I've got an FPGA.
Windows ARM laptops do use UEFI.
What?
Windows ARM laptops use UEFI.
Really? I didn't know that that was used ARM. Huh, okay, the more you know. So you're probably familiar with one of these. UEFI is kind of the more standard one, not standard, but has superseded BIOS and kind of the preferred way to boot. When you turn on your system, this is going to get loaded by the boot ROM, and it's going to start looking for an EFI stub that it can load into memory. So that's where you get to your second stage bootloader. Most commonly, this is grub, but you could also have systemd boot, or you could just have a unified kernel image. As long as it's an EFI stub, your UEFI can probably find it, as long as you put it in the right place. If you're using grub, here are the configuration files for grub and the EFI stub. So you might see when you're updating your system that it mentioned a couple of these. So that's how you would that's how you would update how it knows to find kernel images, because the first thing grub's going to do is go and find these kernel images. But unlike UEFI, it's not going to scan for them. It is already sort of baked in with kernel parameters and where to find the kernels. So if those entries haven't been created when you installed your system, it's not going to find them. Some of you guys might have ended up in that situation before where your grub just doesn't work. It's unfortunate, but it happens. All right. So then you end up at the kernel. So the kernel is usually loaded in two stages. There's the core kernel image, which is going to do like the very base stuff it needs to get the system running. It's set up the MMU, some basic system checks, maybe even turning on certain memories. And then it's going to load the initram fs. This is a in-memory file system that contains important kernel drivers. And at that step, that's where it's going to start initializing all the drivers. And the way it knows that what devices it needs to initialize is it's a requirement for Linux that when you boot it, you hand it a pointer to a device tree blob that contains a tree hierarchy of all the devices that are on the board, at least all of the ones that are kind of the core devices. It doesn't have to enumerate all the USB devices. As long as you point it to like the USB controller, you're fine. You might see an initRD around. That's an old format based on an in-memory block device. Debian might still be using it on LTS releases, but it's kind of deprecated and not preferred for new systems anymore. I skipped a slide. Don't care about this. This is how you make your init RAM FSS. After writing this, I'm starting to realize I don't care about this that much. When you're updating your system, you might see it update this. So here's an example on a Debian system. It's creating that initial file system. That's needed anytime you touch the kernel or any of the user space tools that are used at the kernel during that boot phase. So that's why it's generating those for you. You don't ever have to touch this, generally. On Pac-Man, it looks like this. You've probably seen that a couple times if you use Arch. So I kind of talked about some of these already, but I guess we can recap them. So it loads kernel image. Kernel images are always compressed, so it's going to decompress itself in place, set up memory management, central device. We already talked about this. Probe and log. So this is when we get to, well, actually, this is an interesting one. It has to throw away its temporary file system and actually mount the root file system. And it's at this point that it loads bin/init. And this is what we call PID1 or the init system. Which brings us, and if you really cared, you can look at your journal, and this is, you can see the boot process in real time. So this is where it's trying to unpack the root file system, and where it finally gets to init and calls the init process. So init is the first process that's started by the kernel in the user space. It's the root of the process tree. Every other process is going to spawn from it, and it needs to run until the system is shut down. It's the first thing to run. It's the last thing to exit. Not sure why I thought this was important to be here, but yeah, if you orphan a process, it's always going to be adopted, you might say, I guess since orphan, adopted by the init system. And if you're on your system, you can actually see what you're running right now as init. Oh, wait, I entered this. Why did I put that in that order? Okay, so I'm going to come back to this. Wait, no, actually, that makes sense. So systemd is an init system, but it's way more. Systemd is not just an init system, but also a large suite of user space tools for managing Linux, you might say. I didn't put slides for this, but I'm going to kind of motivate why it needs to exist. So you could write programs that only depend on the kernel's ABI, right? All you need to do is file IO. You know those system calls. There you go. But the problem is software has gotten a lot more complicated, and trying to manage lots of different permissions, trying to do inter-process communication, services, as we'll talk about, it becomes really difficult for all of these processes to try to communicate with each other instead of through a common interface, and trying to recreate from scratch what you're going to be needing that systemd has anyways. I'm not going to talk about systemd versus other init systems. I know that some people don't like systemd. For the sakes of this conversation, we're all pro systemd here, all right? We're just going to explain it and learn it. So is your system running systemd? Well, there's a pretty easy way to check this. If you just check what is running as process 1, you should see systemd. And you also can look at what's symlinked to bin/init, also going to be systemd. I imagine probably most everyone in this room is running systemd, unless you're running something like 𝗟𝗵𝗀 or Gentoo, maybe 𝗍𝗿𝗲. I bet Nix probably could be configured not to use systemd. It's required? Okay. All right, I stand correct. I've never used Nix. All right, I guess I should have done my research. Oh yeah, it's just, I think 90% of the people though, who I know who use Gentoo end up not using systemd. Kind of makes more, are my slides, why are those, that's not centered. Wait.
Is there a new line in your types config?
No. It was just over zoomed. Okay. That's annoying. Well, we're going to proceed. So we're going to talk about these 5 and maybe 2 others I didn't put there. Core systems of System D. Here they are. I'm not going to list them all out or read them all out because I want to keep moving. So the fundamental, like, atomic element of System D is called a unit. And the core responsibility of System D is to manage these units and their dependencies. And usually these are stored inside unit files. There are some in-memory ones, but lots of them have files on your file system that describe how a unit file is supposed to run and what it's dependent on. So there are like 3 main types of unit files I can think of. Ones that come with System D, these are core System D services. We'll be talking about journal D, login D, etc. Other softwares will install their own unit files. Here's some popular ones you might think of, especially SSH and Network Manager. Most people will have that. And then you can also make your own, and automatically, why did I include my own? All right, and there's also automatically generated ones. Believe it or not, things like mount points and devices have unit files associated with them. Obviously, those things still exist in their literal sense, but the unit kind of encapsulates them and describes them to the larger system. And the naming format for these is usually name.type. So you'll have a .mount or .service, which I have enumerated over here. So there are, I want to say about 11. Let me count them, actually. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, no, 14. Or 13 if I miscounted. Different types of units. You have services. I'll just name all out because I think they're all kind of important. Services, they start and control daemons and other related processes. Probably the most common one you see, right? Your SSHD process. Almost everything that ends with a D stands for daemon. There's sockets. Sockets use one of these protocols, IPC, network sockets, or a file FIFO, to activate some other unit, right? So a popular one you might be familiar with is that Docker has a socket, so you can activate the Docker service by communicating with the Docker socket. There is also targets. Targets help you collect multiple units into one and can help you trigger things on certain events. Devices, like we mentioned earlier, each have their own unit type, own unit associated with them. There's mounts, which are the mounts on your files. I actually don't know exactly what an auto mount is, but I put it in there. It's probably important. There's timers. This is when you want things to happen at a regular period. That can be used to activate other units. Swaps and paths. Swap is just kind of like, it's treated a lot like how mounts are. Paths are interesting because they allow you to have certain events on certain paths in the file system trigger other units. That could be very useful for something. We have an example for that later. Slices is probably one of the ones people aren't familiar with. Slices are how we organize processes into C groups, which is for resource management. Each user will be given their own slice and manage under that C group. And scopes are like services, but they don't spawn processes. They manage some other foreign process. Yes?
And I do just want to point out, just in case someone doesn't know, that a daemon is just the name of any process that runs continuously in the background.
That is correct. I didn't think to have to explain that. Yes. You are correct. I don't have anything else to add to that. Almost all of these are daemons, so that is good to know. I think, yeah, so at a high level, this is what System D does when it first starts. The very first thing it's do is going to scan your file system table and mount anything that is a mount point or swap file in there. And I actually think you can get away with not defining the FS tab if you declare your mount points as a unit file in System D directory. This is
The most System D build thing I've ever heard.
I think the only reason it exists today on System D services is for backwards compatibility reasons and legacy reasons. Yeah, because I think you don't depend on it for your niche. This is before Fuse. This is your core, like actual mount systems that are defined in your file system. Fuse is added on later.
Fuse partitions in your FSAT.
You put fuse what you do?
Yeah, if you want to.
Okay, sure.
Well, my point is that if you can put them in your SSM, you can probably put them in system D units.
Yeah, that's what I was saying, is that your system D parses your F.
You could put fuse drives in there. It does.
Okay, yeah, I guess. I would never have thought of to do that because they're not really needed immediately at boot time, but
GNOME uses it to manage user around this too.
yes, but those are usually managed once you get to login D later.
That's true. It's usually on user.
Yeah. I don't think at boot time you're really going to need any Fuse file system. But it's a good point. I didn't talk about Fuse at all in this presentation. That's a shame. It's going to generate all those device units for a lot of devices, mostly the ones that you might need to interface for the user space. Then all those units that we were talking about earlier as examples, it's going to start spawning those. And then it's going to start login D and drop a TTY. Or if you have a display manager, it will launch that. So that's sort of the boot up process. And then once you're inside systemd, then you're at liberty to start inside. Once systemd has been initialized, you're at liberty to start controlling processes. So, oh, what's this? There's 3 main places you can put a systemd unit file. There's actually probably more like 10, but these are the ones you'll probably want to use because it searches a lot of paths. If you're doing user local, so things that you want to run with user privileges and don't need to be running for the whole system, I'd encourage you to put that in your local config file. Might as well not give it more privileges than it needs. If you're going to do something that is system-wide, you can use this second one. That's for system administrators. And the third one you shouldn't use at all. That's for packages. You don't want to conflict with packages, so don't put them in there. But it's a great spot to go and find example service files and other types of units. Like the documentation is pretty good for these, but the examples are almost better. So here's some really simple commands you can use to sort of understand what's going on with certain units. So you have print, enable, disable, start, and restart. The difference between start and restart and enable, disable is enable and disable will allow it to be triggered and run automatically based on its rules, whereas start and restart will just run the unit once until it chooses the exit. There's a whole lot more subcommands, but I think these ones are pretty good to get you started. So you could just go right on your system right now and type systemttl, hit enter, and it'll list every single unit on your computer. And if you hit status, it'll also list what their current status is. Very handy, but usually you'll want to be targeting a specific unit. And I'll get some examples later. Oh, and if you're running a user unit, you should use --user, and you can also control a remote system via SSH using the --host option. Although most of the time you're just going to SSH in and then control it from there. I want to get to the examples. Examples are next? Okay, so I have an example. This is a system example. I didn't make this myself. I went and stole it. But I'll have an example that I wrote myself as well. So there is a service called fstrim. This was really popular on NVMe and SSD drives. What it does is it goes and discards unused file blocks on your file system.
You were not supposed to use trim on NVMe drives.
On
Only on SATA drives.
Really?
Yeah, that's what
I thought you're not supposed to use continuous trim. That's why fstrim still exists.
You might be right.
If you mount your file system to continuously trim, you will probably destroy your SSD slowly. This is why they have this service. It's a timer and a service. The timer is responsible for activating it, say once a week, and then the service will run when the timer hits it and then exit. So to see what this example looks like as a unit file, oh, that looks so much different. That was supposed to be the systemd green. That's not the systemd green. Here's the timer, and this is a pretty simple description, right? It says on calendar weekly, accuracy seconds 1H, and then it says to run, where is it? Wanted by timers.target. Wait, no. Where is, did I trim it? It's supposed to run my other thing, unless that's described in the other service. It shouldn't be, though. Let's see what's in here. I must have trimmed it out. That's weird. Well, anyways, this will activate this service, which here, instead of just being a timer, it actually has something it's executing. It says exec start, and that's fstrim, and it will scan your file system table and trim anything it finds in it. Do you ever figure out whether I'm supposed to be using trim?
Yeah, you're only supposed to use continuous trim.
Only?
Or not, sorry, a non-continuous.
Okay, yeah. So there's a lot of options for how you run a service. Not going to explain them all here, but they're really well documented in the man pages. So this is just one example of a system service that you can run. Here's a much simpler, and if you want to know what happened, you can quickly just go systemctl status, like we mentioned earlier. It'll show that it did run. In this case, it ran about 4 days ago. I think mine's set to run on Mondays. And then you can also look in journalctl, and it'll show it activating the service, deactivating, and done. So exactly as we would expect. And also, this is much better than cron if you're thinking about using a cron tab for this, because cron is a lot less reliable when running long term. It's not guaranteed to activate at a regular interval if your system isn't fully up all the time, whereas this will handle that perfectly fine. Here's one I wrote myself. So this is an example's user service that will automatically mount my Proton drive to my computer whenever my network status is online. So it's pretty simple. It has a dependency. It wants the network online, and after it's online, it will trigger this. So it runs rclone mount, mounts my Proton drive inside my remotes folder, and will automatically restart if it fails, because this command does not run in the background. You have to explicitly tell it to, so that keeps the service up and running. So that's one kind of useful example of a daemon you want. So now I can take my laptop anywhere, and as soon as the network's back online, it will restart that service for me. Continuously run?
Yeah.
What do you mean by that? Like,
So the network's online, it's just gonna like constantly check to see if the network's online.
that's a trigger. It's systemd knows when network comes online. It's an event that happens. Yeah. And also, this will not relaunch unless it exits. So once this is online, it runs until it terminates. And then if the network comes back online, it will activate it again. I will say, this is still in beta. Rclone support for Proton drive. It's a little bit finicky, but it's not terrible. It just because it's end-to-end encrypted, it can't really cache things the same way it would with other files remotes. So the way I started this is first thing you run is daemon reload. This will rescan and update any units. You have to run this before you can start a unit for the first time. Then I can call start, and then assuming it doesn't return a non-zero exit code, that means it's running, and I can look at status, and it's loaded and running, and we're happy. And if you're running a thing as a process as a daemon, I'd encourage you, I put the -v flag for verbose. You should always put your verbose flags on, at least at a reasonable logging rate, just so that your daemon gets systemd logs, so you know what happens in the background. Here's some basic power management ones. I bet 3 of these you know and 1 of them you don't. So power off, as you might expect, reboot and suspend. There are other commands like power off and reboot that are just one word. Those are actually just symlink to systemd if you're running systemd. So this is the real command. One nifty one that I use every once and often is called soft reboot. This will just reboot the Linux user space. So if you ever get in a weird spot where, say, your desktop environment is going finicky, but it's not a kernel panic, it's not a driver failure, you can run a soft reboot and it'll take you right to the login screen, and you don't even have to reboot your full system. It will just restart it from when the kernel loads the init system. It says that they're subject to the login inhibitor lock that we discussed earlier. We're going to discuss that later, clearly. I reorganized these slides. Oh, is that a hand over there?
Yeah, I just want to say I used to apply sometimes for systemctl reboots, just --firmware setup, which just reboots straight into files in case you don't want to bother with the
I didn't know that, and thanks for sharing, because I hate spamming everything on my keyboard because I always forget which laptop has which BIOS key, and it drives me insane.
Windows too, if you hold down Shift and press the restart button.
I just beg and pray when I use Windows. Thankfully, I haven't had to troubleshoot Windows that much. I just reboot it and hope it goes back to normal. So that's some basic power management stuff. So next thing I'm going to talk about is UDEV. I actually got really frustrated trying to prepare the UDEV stuff because I could have sworn, it's going to make me seem incompetent, I could have sworn you could run user space UDEV rules. Like in .config/udevs rules D. I could find no documentation on it. I don't know. I guess it just doesn't exist. I could have sworn I've done it before. Because to me, it makes perfect sense that you might want to trigger a non-root process based on a UDEV rule. And there might be certain things that just don't apply to the whole system. But couldn't find it. If anyone knows, please tell me.
I am pretty sure that user space UDEV rules do not exist.
Why not?
I don't know why.
Like, I couldn't figure out what's the security implication. You can already sniff every single UDEV rule that goes by. I'll show that command later. Like, there's no security implication as far as I'm aware.
Because you can just add arbitrary UDEV rules.
But they'll still run as user privileges instead of root. Kind of like you can make user system D services.
UDEV rules that allow for user space direct access to USB devices.
Yes, but I want to run a UDEV rule without ever using root. I want it to be written to a file owned by the user and not scoped to the full system. Yes?
I believe the idea that he's trying to get at is that a malicious program could install like a sniffer and start doing actual things on your behalf if you could make
Yeah, it's one thing if
You can already do it, though. I'll show you. So you could do it, but it's not supported by UDEV natively. So I guess I got to back up. I started talking about UDEV. People might not know. UDEV is a user space device manager for Linux. It existed before systemd, but it's been adapted into the systemd ecosystem. The primary interface for using UDEV is writing these things called rules, which will run. It's essentially this list of rules which take some sort of how do I describe them? They are fed events and then conditions on those events, and if those conditions are met, they run a certain executable. That is the most basic use of them. They might be able to do something more fancy, but that's how I've always seen them done. If you're trying to create system-wide rules, there's the directory for it. And then system-wide software and styled rules right there. But like I mentioned with the systemd services, I don't encourage you to put them there because it might conflict with other things that your package manager is installing. So here's an example of a UDEV rule I wrote. By wrote, I mean I stole off online one time. It adds a group to a backlight subsystem. So when it detects a new monitor with support for backlight controls is added, it adds this group, which I'm added to, and allows them to control that. So that allows me to change my brightness without having to use the root privileges. It's probably one of the most common things to use UDEV for. And we'll also talk why this is actually not necessary for a lot of things now because of how login handles things. But you can monitor and sniff, this is what I was talking about earlier, every single UDEV thing that happens by running UDEV ADM monitor. It will print out every rule, every action that happens along with all these properties. So this is really good or very useful for debugging a UDEV rule if it's not behaving the way you want, or if you're just trying to figure out what to make as a UDEV rule, right? So like right now I could, so this was me actually plugging in a USB keyboard. So if you want to figure out how to write a UDEV rule based on a keyboard, you can run this, unplug and replug in your keyboard, and it'll spit out all these events. And now you know what properties to look for to match your event with. So this thing goes on forever. So you see gaming keyboard. So if you want to only do stuff when you get gaming keyboards, you know, now you know.
your keyboard is just called USB-HID gaming keyboard.
Yes. That's the model encoding. I don't know. It's stupid. But that's how it's done. And this is actually not when it's added, but when it's bound. And I will mention that it's actually really useful to use the action bind instead of add, because sometimes when you add something, that's when the kernel sees it. When you bind something, that's when systemd adds it to your seat, which we'll talk about later because login D is complicated. And probably login D is the only part that people aren't familiar with. So this is my frustration with why you can't have user space, not user space, but user local UDEV rules, because you can already sniff every single UDEV event. So I don't see it as a security problem.
When, on the previous slide, when you were creating a UDEV rule to modify the brightness of monitors plugged in,
Yep.
does this require the monitor to support certain brightness controllers? Because I know that monitors that only talk over the DDC protocol need a completely different subsystem.
This is different. This is for my built-in laptop backlight. I have separate stuff for DDCI, DDUCI. Is it DDC util? Oh, what's the protocol? DD/C, DD something.
It's just DDC.
Oh, I thought it was like 4 letters. Okay. All right. Huh. Yeah, that's completely different, and you probably have figured out how to give yourself permissions to access that without needing root.
Yeah.
Yeah.
It's kind of yes, but it's just UDEV rule.
Yeah, it's not that bad, but now you know that you can do it through a UDEV rule. I know. I guess maybe I should have gone through more examples to kind of motivate this more, but I ran out of time for the UDEV rules. I talked way too much about login D, or I'm about to talk way more about login D. Login D. Okay, so this is probably the one thing that people never have seen before, because if your system's working right, you never have to interact with it.
Yeah, not my germ on that.
Oh man, I love having to manually unlock my computer with login D when the session locker on KDE inevitably fails for the 40th time today.
I guess I've never used KDE, so I don't know what that feels like. I I don't even use a display manager. What is questions? No.
You don't use a display manager?
I get the login TTY. Just type in and then write start. Type start X. Starts
Oh, you type in start X.
the start X. Yeah.
Okay, fair enough. Yeah. I don't use X.
But there's something really bored on the X and Z get inline image, so it would keep going to sleep, and then I would have to I forget exactly what I had to do. I had to go to a TTY to get back into the session where DD was running when I was backing up the drive once.
Yeah, and you can always do that by doing Control Out, a function key, to get to a TTY. That's all stuff managed by login D as well. And I'll be honest, I don't use a display manager because I tried 5 of them and I hated all of them. And I guess I have to agree with William. I had so many buggy problems with them that my life just better not worrying about it.
Anyone here use 𝗏𝗏𝗏𝗏𝗏?
I might be able to
How is reading?
𝗏𝗏𝗏𝗏 is pretty good.
It's a pretty fun API, actually.
Greet D is an alternative to login D, right? It doesn't depend on.
No, 𝗏𝗏𝗏𝗏 is
like
a display manager.
Greet D is like LightDM, but it works.
Huh, okay.
One of the greeters is like that. The idea
No,
behind
LightDM is a modular greeter.
Oh, okay, never mind.
Yeah, 𝗏𝗏𝗏 is by default it's a terminal only thing.
You can tell it to use a different greeter. It's like LightDM.
I used to use LY, I think that was called.
Yeah.
That worked pretty well. Didn't offend me anyway. That's also just like a TUI type
Disk
interface.
space, I have 170 megabytes remaining.
It's a lot. So login D is responsible for user login management. So this includes authentication and user permissions, user permission management, user permissions on hardware and other things. So when a user logs in, login D is going to do several things. Very first thing it's going to do is to create a new user slice. This slices are associated with C groups. Do people know what C groups are? No. So in the Linux kernel, C groups is a way of collecting processes together, putting them in a group, and restricting their resource allocations. Like they can control how much they get scheduled, how much memory they're allowed to use, how much disk I/O. So containers are also given C groups and isolated that way. And they also, what was that?
Is there any reason for me, a normal user on my computer, doing normal user
I'll be honest, I don't think C groups are terribly useful to begin with because they're mostly for resource management. Because they're not like namespaces. Who knows what namespaces are? Okay, namespaces actually isolate processes such that they can't see each other. Right, that's why when you go into a container, and if you remember from my Docker talk, you go into a container, you type top, it only sees what it's running inside the container. That is what a namespace is doing, not a C group. C group is for resource management. I have never created my own C group before. I've created my own namespace, but I just don't. The only usefulness I see of a C group is trying to protect root processes from starvation of the user space. So when the kernel starts to see things are going wrong, they can restrict less privileged C groups from using as many resources so you don't starve more privileged resources. But I don't know as much as I should. Anyways, the other thing it will do is it will create a seat, as it's called. A seat is associated with a user and also contains all of the devices and permissions it's allowed to do. And then it'll create a session. You can have multiple sessions per seat, but for the most part, unless you're using like SSH, you're just going to have one session. Each time you connect into SSH, it'll create a new session, and when you exit, it will disappear. But if you use something like tmux, then it creates a daemon, and it gets adopted by the init system, systemd. Doing some callbacks, seeing if you guys remember. So here's some stuff that you'll probably never use. If you want to troubleshoot your login status, you can list your seats and sessions, show them. Maybe the only one that is kind of useful is logout. If you were to, say you are in your desktop environment and you call, say you're running i3, you pkill i3 and then exit, so you're back at the login screen. That doesn't log you out. That session is still authenticated, and it might still be running processes. That's not a sufficient thing. Just because you've closed everything and you come back to the login screen does not mean you're logged out. So probably the buttons that you're running on your desktop environment will be calling these in the background, but it's just important to know that it is calling these. It isn't just simply closing itself. It does need to cleanly terminate the session. I put a bunch of IDs in there, but if you just omit them, it'll use the ID that is associated with the process you ran, which is probably going to be the only one that exists, because unless you have multiple users on a system, you're not going to have multiple ones. There is one interesting thing here. Some people might not know this, but all these groups that you see listed here, if you're running on a systemd system that is set up properly, shouldn't be needed anymore. This is because systemd does not depend as much on groups anymore because it now has access control lists. It will go in and manually add you to the access control list for various devices that you're allowed to access. This is done by login-d, and you can change the configuration if you need. So beforehand, you might need audio or video to be able to control audio and video devices. If your systemd is configured correctly, then you shouldn't need these groups anymore at all. In fact, if you read the Arch Wiki, they say that being in the audio group can actually cause more problems than good nowadays. The rest of them should be fairly safe. They won't cause any problems. But it's kind of nice to know that you don't need these anymore. And I can actually show you that you don't need them anymore. So if you go and type seat status, it will list out your current seat and all of the devices associated with it. Once you see that, maybe I should be showing these, but you guys got laptops, you can do it. You can then type get FACL. This is going to get the access control list for files. Recurse it and skip the base. Skip base means skip anything that doesn't have anything added on top of it. Just print stuff with modified access control lists. And you'll see on device that you've been added to various devices. Things such as audio and video, I2C, and probably other stuff that you could configure if you modify your login-d config. That no one is probably ever going to do. But the default config should, make your system work, hopefully. So, what does the -- help say? Is it? There's definitely -r. That's for the recurse.
Oh, it's dash recursive.
Cursive. Oops, I'm going to have to update that. But for all you guys doing that, you should see a bunch of files listed out, probably frame buffers and SND for sound devices. Inhibitor locks. We were talking about this. Well, actually, I don't think the thing that we were talking about earlier was actually an inhibitor lock. It might have been just cleanly shutting down. But an inhibitor lock allows you to do one of two things. It can allow you to either hook when a certain power management event happens, like a suspend or shutdown, or it could even prevent it. Now, there's usually ways to overwrite the inhibitor lock, but at least it's a good warning. If someone goes to shut down, it will say, no, you're going to have to tell me to force shutdown. One reason you might want to do this is to prevent your system from getting corrupted. So here's an example. If you're on Arch and you're running Pac-Man, if you run with the systemd inhibitor lock, it will prevent the system from sleeping or shutting down while that command runs. If you were halfway through updating your system, you could end up in a corrupted state. Right? Now, luckily, for most of it, you're just copying over files. So I guess you could get unlucky and be somewhere you shouldn't be. But you could actually mostly recover. But there are some things that would be sort of detrimental if you interrupted the process. It would be a very unlucky window to get in, but it can happen. So I don't have much to say about that other than that you can do it. And there's even ways that you can write hooks into things like APT and Pac-Man to use inhibitor locks. I've seen some examples online. I didn't write one myself because I ran out of time, but you can definitely do it. Now I'm going to talk about Journal D. This is probably the one you all know about, so I'll just run right through it. Journal D is a systemd provided service. Yeah, I did that right. I thought I was wrong. That provides logging for events, both the kernel ring buffer, that's dmessage if you've ever done that manually, as well as systemd itself. This is kind of useful for finding potentially problematic events, diagnosing an existing system failure, or monitoring changes in your system. If you're ever at a state where your system's not behaving the way you think it should, go to Journals D. It's probably going to get you at least some idea of what's going on. It might not solve it right away, but it's your first diagnostics tool you can use. And it's really simple to use. You probably used it before. Here's just a few ways that you can use it. The most common ones that I use is --boot 0. That will start the log from your last boot. You can also do minus some number to go previous boots ago. Reverse is kind of useful, but I like follow more. If you open that, it will constantly print out the log. So if you're going to go do something and you know it might create a systemd thing and you want a systemd event that is logged, you might want to open that so you can see it happen in real time. And there's some other options there. They may or may not be useful for you. But there's lots more options for filtering and outputting, so just read the man page if you want to know them. You might get this warning. By default, you can't read kernel messages. There could be some secure, I mean, you probably shouldn't be logging secure things in general, like credentials, but there's probably some security things associated, so you have to add yourself to the ADM group if you want to do that without being root. And then you'll have to log out and back in, which you know how to do manually now, if you want to, if you hate yourself. So here's what mine looks like. So you can see ADM right in there. I actually don't know what the default configuration is for all systems, but I know that on a lot of my systems, Journal D was not configured to have a maximum size. So it grows indefinitely until it takes up many, many gigabytes. It also didn't help that I turned my Journal D up to very verbose because I like to know when shit happens. So if you want to prevent this from happening, you can go in. Well, first of all, I guess it's on the next slide. You can manually trim the log. So here I have an example of deleting anything that's older than 7 days or only keeping the ½ gigabyte most recent stuff. Those are two kind of useful commands I've used sometimes. But you also can go inside your config and set the maximum size, and it'll automatically prune it as new stuff comes in. So in this case, set max usage to 1 gigabyte, which should generally give you enough time that you won't lose anything important. As usual, man page also has all the information you can need. You also can manually log things to the journal if you want using systemd-cat. So here I cat a test message as a test process, and it'll show up there. If you were going to be writing like a C program, they have header files for doing this, and you don't need to, pipe it to a bash thing. But if you're writing a script file and you want to report something, it's a good way to do it. Although if it's running as a service already, it will get piped, like as a systemd service. It'll already get, the output will already get piped to the journal anyway, so you won't need this, but it could be useful in certain situations. dbus. So dbus, I'm not sure why I'm so excited for this one. So dbus, aka the desktop bus, is a message-oriented middleware. So it existed also kind of like UDEV before systemd came around, but it was adapted. I guess adapted isn't that it wasn't absorbed, but it's a protocol used inside systemd for inter-process communication. So yeah, it was originally implemented by the Free Desktop project for the GNOME desktop, but I already said that. Yeah, so it facilitates inter-process communication via Unix sockets. And there exists a central dbus broker service that started when your system starts as a systemd service, like we were talking, and that runs in the background and allows you to communicate these messages between processes. This is also another one of those things that if your system's working right, you should not have to know that it exists, but it's kind of cool to know that it exists. So if you were running without dbus, you might imagine your processes trying to communicate like this, right? They have to manually go and search for other processes and try to open connections to them, which is just inefficient, arguably less secure, and just non-standardized, and just makes the whole user space a terrible experience as both a developer and a user. dbus tries to centralize all of this on a standard bus with a standard protocol that everyone can communicate on. I guess I didn't even walk away. Like everything else we've talked about, you can sniff everything that's going on. So you can run dbus monitor, and it will print every single dbus message that happens in your user space. There's two separate instances of dbus, one that's running in your system space that you have to be root to access, and one that's running in your user space. That's for just your user processes. This will be your user processes. So probably most of you, I don't think this is X specific, you can call notify send, which will send a message that's meant to be a notification for your desktop. If you have any desktop environment, KDE GNOME will have one already installed. If you're using like i3, a lot of people will use something like Dunst. This will produce a message. The way that that gets to it is through dbus. So here I call dbus monitor, notify send, and you will see the output. I wonder if I put it here. Yeah, so it actually spits a whole thing because there's kind of a handshake protocol that goes on. But you'll see here some metadata about it, but then, what did I send? Does anyone remember what I sent? Oh, yeah, that's right there. I should have used something that stood out more. Yeah, I sent systemd. There it is. So any process that was listening on this bus could take that and take a certain action. And there's a lot of other types of processes that use this dbus. I think I list some here. So the one I'm most familiar with, because I've done some development using it, is the 𝗟𝗶𝗸 interface. You'll probably notice that if you open something like a music player, Spotify, or whatever local player you have, your desktop environment automatically knows that you're playing something in the background, right? And it might even offer you pause stuff, pause controls, seeking, and it even integrates with your audio playback tools, allows you to change the audio volume for different streams. This is mostly done over 𝗟𝗶𝗸, which is a dbus protocol that's standardized for video audio playback. But there's all sorts of other ones that are done. I've noticed networking ones, key rings, secrets, and we just showed a notification example. Let's see what else we got here. What is this? Oh, yeah, you can list out the connected buses you have on your system. So you can see here, I was writing this at the time, so I was listening to music on 𝗂𝗏, viewing it in 𝗣𝗐𝗂𝗲. I had Flameshot open. Notifications was being listened to. These are all the things. What? No, 𝗂𝗏. Media player 2.𝗂𝗏. Oh, viewing my PDF. Sorry, on 𝗣𝗐𝗂𝗲. I actually don't know why 𝗣𝗐𝗂𝗲 needs a dbus protocol, but maybe it needs it for LSP. No, I don't think it would. I'm not sure. I've noticed I actually really abbreviated this list. There was a lot more. And some of them kind of surprised me that they needed dbus connections, but it's there. Ooh, and one thing to say about security here. So by default, there is no isolation for dbus other than your user space and your system. So that means any process can listen to what's going on the dbus, which makes me really surprised when I've seen people forward their dbus socket to a container, like a Docker container. That just sort of ruins the isolation of your container altogether. I'm not sure why anyone would ever do that. It is convenient if you need to do certain things, but it kind of just ruins the isolation that Docker would provide. Wait, what's the difference between these slides? Oh, that just listens the names of the system processes. So here are some system processes that use dbus. And wow, I actually got through that really quickly. That was only 45 minutes. So anyone else have any questions, comments? Know a little bit more about systemd. I sort of wish I wrote more about systemd administration stuff. But I kind of hope that at this point people kind of understand more about how their system operates and how they can interface with it to solve problems. Yes?
Kind of more of like a useful trick, I guess, but how you have to start a service explicitly and then enable the system service also explicitly as two separate steps. You can do that at the same time if you do systemctl enable --now with the --now flag that just enables the service and it starts it at the same time. So you don't have to run two commands.
That's pretty nifty.
Did you not know that?
I've never done it. I mean, I usually only have to enable a service once, so it doesn't really save me a bunch of time, but it's useful to know. What is that?
Any application, any process make an inhibitor lock?
Make an inhibitor lock? Yes.
So if I wanted to be
A dick?
very, and I could just make a normal application, give it an inhibitor lock saying it can't shut down, and then you try to shut down, it's like Windows where it says like
So
waiting
usually
for
most
processing.
desktop environments will ask. They'll be like, "Are you sure you want to shut down?"
Inhibitor locks can always be overridden.
Yeah.
Okay.
So you actually saw this. When I tried to put my laptop after we were watching a movie to sleep, it said that I couldn't sleep because another user was logged in via SSH. That's what that was. And all you have to do on the sleep command is add -i for ignore inhibitor lock. So I'm not sure if the inhibitor lock was held by a process of higher privileges, whether now you couldn't. I'm not sure, but you could definitely override it. Yes?
This is just like a cool command just systemd analyze is pretty cool. It just shows you how long it takes everything to do.
Mm-hmm.
Time, you want like more granular view, you do systemd analyze space hashtag void. Pretty sure that tells you like how long each takes like each service to start. So if you want to like minimize the time,
Yeah, find all those services that you forgot you installed that are running, such as mounting Proton drive in the background for no reason. Yes.
So what about dbus makes like it more efficient than like the example you gave?
So let's say you're writing a piece of software and you want to send a notification to the desktop to show for the screen, right? Like, say you wrote, what would be an example? Like Discord sends messages, notifications. The problem is you have no idea what software you're running as the notification center. It could be GNOME, it could be KDE, it could be Dunst, it could be a list of another dozen things. So instead of having to scan for each of those processes and know how to communicate with them individually, they standardize a protocol for messaging, and you just send it to the bus, and if any of those exist, they'll pick up the message and handle it. Yeah, and I guess that one doesn't matter as much because that one is kind of just a tree. There exists one person who's going to listen, a bunch of people who will send. But the Empress example, that one's a lot more complicated because you might have multiple music playback things, lots of software that might interact with it. That's a more many-to-many connection thing that would benefit a lot more from dbus. Yeah. And actually, the kind of entire motivation for systemd in general is to try to standardize more of the user space because, like I mentioned at the beginning of the presentation, just depending on the Linux kernel API is not enough tools to make useful software nowadays. And having a more standardized user space will make developers' lives so much easier. All right, yay. Is there anything that feels like I missed, like entire subsystems of systemd? Thermal D?
I have no idea what that is. I'm just looking at the picture right now, and I don't know what it is.
I know I didn't go in detail about the authentication systems like libpam and ALPN. I don't know how all of that works.
Yeah, I don't know. I remember you can't log in without LibPam at all.
Yeah, I think it's an essential library. Yeah?
You don't need to reload systemd for it to notice new services anymore. You do have to do it if you change it, but if you create a new file, it'll automatically handle it.
Huh.
Which is interesting.
I would have thought it would be the opposite. Once it's like registered the file, it wouldn't. Huh.
You have to reload or restart. In which case,
Oh, I guess if it's already running, yeah.
no, it already has like enabled it. It doesn't have to run it now.
Huh.
Enabled or if it's already set it up and you change it, you do have to reload or restart it.
Well, that's good to know. All right, I'm going to stop the stream, but you can ask me more questions if you want.